Hello ladies and gentlemen, it's good to see you again. Thanks for tuning in today for what is the 13th lecture of GGS 300 Quantitative Methods for Geographical Analysis. Today we're going to be covering one of the most important topics within statistical analysis, correlation. So where are we within the current coursework? Well, you've had one assignment set for you, which is due, it's going to be due on November the 25th, so in a couple of days' time. I hope you managed to get that in on time. That's an important one, so that then we're able to basically finish the remaining two assignments in the last couple of weeks. So there is another one that will be set today, which will then be due on December the 4th. So reach out to me if you've got any queries or any of that, but it should be fairly straightforward by now. So what's the plan for the rest of the class? Well, essentially we're going to have correlation today, and then we're going to be focusing on regression in the last lecture that we're going to be covering. So that's essentially how the next couple of classes are going to actually pan out, and I've already covered the assignments that are going to be associated with those lectures. And there will also be the final exam for which the date hasn't been set yet, but it'll be similar in kind of scope to what we've already seen, but it will be semi-comprehensive for what we've essentially covered across all of the term, but then focus very much also on the last couple of lectures that haven't been fully assessed yet. So I think this is an exciting one for me because, you know, most of what we've done through this term has been quite introductory at times, and then by the time we started testing samples, a lot of those tests are, you know, they're used a fair bit, but they're also a bit esoteric at time. And ultimately, the key statistical techniques that most people are going to be using on a daily basis are probably going to be correlation and regression for many different types of academic areas. So if you go into your standard economics faculty, the econometricians will be using regression on a fairly standard basis. If you go into engineering, computer science, regression is used as a common technique. If you go into the social sciences, then again, regression is one of those bedrocks, correlation is one of those bedrock methods that is used throughout that entire area, whether it's, psychology or psychology, or, obviously within geography, if we're interested in understanding geographical features as they exist in space. And that's because this is a really fantastic way to understand how different metrics vary together. And once you understand how metrics vary together, then that can give you a good way to understand the world. It helps you understand, help develop new knowledge. So it's really important what we're going to be covering in the last two classes, and it's really going to round off everything that we've learned in this past term. So hopefully you're going to go off having succeeded at this class, and then if you take further quantitative courses, you'll have that really good understanding of how to do correlation analysis, regression analysis, and then if you have to pick up research topics, for example, for a dissertation, or you want to go on to a PhD, this is going to be a pretty important tool that you want to have in your methodological toolbox. So I'm not going to cover this in too much detail. You know what I have to say about this. So we did descriptive in the first part, now we've moved on to inferential, and actually we've covered really quite a wide range of inferential statistical tests. Now, maybe not in a huge amount of detail, some people specialize their entire careers in one or two of these techniques, but we've covered a wide variety of techniques across this course, and I think it's actually been a good introduction to the landscape of statistical testing. I hope you feel the same. So I am going to return back to Gerwin's flowchart for selecting commonly used statistical tests, and that's because we've pretty much done most of this now. And I think it's exciting for us because we've covered a variety of the continuous tests. So we covered the t-test, the Mann-Whitney U-test. We then did ANOVA, so analysis of variance testing, both the parametric and also the non-parametric Kruskal-Wallis approach. We covered categorical testing, so up here in the top right-hand corner using chi-squared, and we did a bunch of difference and difference tests as well. But where we haven't really got is down here, so understanding continuous data metrics, but asking questions about relationships. So rather than differences, we're thinking about how different changes in different variables relate to each other as you vary them. And what does that mean? Well, we're going to cover that in this particular part of this class. So we'll do regression analysis next week, correlation analysis. Today we're going to focus on Pearson's correlation coefficient, Pearson's R, and then the non-parametric version. So when you've got non-normally distributed data, Spearman's rank correlation. Okay, so I hope that that's kind of drawing a close now to this kind of landscape of statistical tests that we've covered already within this module. So the nature of correlation, let's think about covariation and the strength of different relationships. And ultimately, so far, we focus very much on taking a sample. Maybe we've gone out and we've decided that we want to sample house prices, or we want to sample socioeconomic effects of different neighborhoods. But generally, what we've then done is we've kind of compared these metrics that we've achieved to other population parameters or to other samples, okay, to understand whether potentially they're significantly different, for example, and whether then we should think more broadly about how that data has been collected and why it might be different. So generally, that's not what we're going to be doing here today. Obviously, that's focusing on differences. Now we're going to start focusing on relationships between different variables, okay? So we're going to be moving from differences to think about similarities. So we can do tests with correlation analysis, and that's interesting because then it helps us understand two different things. Okay, so with correlation you can understand the direction of the association between two variables, and that's either positive or negative essentially. And then we can also understand the strength of different associations. So is it a strong positive correlation, or is it a weak positive correlation, or vice versa, a strong negative correlation, or a weak negative correlation, or maybe there's just no relationship at all. Okay, so this is what we can essentially start to understand by using this specific set of methodological approaches. And it's very handy. It means you can pretty much compare anything that you would like. They don't need to be in the same units. You just need to be able to actually pair two data metrics together, and then you can just go off and plot them basically. So I think we did actually cover scatter plots within some of the early introductory work. Maybe you've already covered scatter plots in previous modules or classes that you've taken at GMU or elsewhere. But really, this is going to be a key way to understand how different entities vary across space, across time, or just with each other. So I had a mentor who was actually a senior postdoctoral researcher at the time when I just started doing my PhD, and he was very experienced. He was, maybe 10 years older than I am now, so he had a lot of experience. He'd come from physics. He moved into this kind of climate science technology area that I did my PhD in early on, and essentially he was trying to understand how different policies on the transportation system would affect decarbonisation. And he'd worked a lot already on energy systems. How do you decarbonize away from fossil fuel-based methods such as coal or gas towards renewable forms of energy, which could be wind, hydro, solar, these types of energy generation methods. And actually, that's where about a third of our energy is consumed, is produced, and that produces about 1/3 of carbon emissions. Then another third of the carbon emissions comes from transportation, and that's why transportation is really interesting. So the question is, well, which policies would enable you to decrease carbon emissions from the transportation fleet, whether that's your car, your personal vehicle that you have, or whether it's from buses or coaches or any type of other kind of fossil fuel-based transportation methods. And what he did, and this is kind of the point that I'm trying to make here, was he started by scraping a whole load of data on engine types and taking a whole load of variables, and he just made like giant scatter plots, so scatter plot matrices of all the different metrics that he had actually for car engine sizes and things like this, and he started to understand the basic relationships. So what I'm going to tell you here, is just the very kind of high-level fundamental theoretical approach to understanding correlations. But even if you're, really advanced and you start on a new topic, the first thing you want to do basically is start to plot your data in this way. Okay, so I make that point here. I say, if you're working on a new topic, maybe a new research area, then what you want to do is start to visually inspect the data, okay? So you want to create scatter plots to understand how these key factors may be correlated with each other or not, as the case may be. Okay, so that's kind of what we want to do. We want to develop correlations to understand the world, then we can develop ways to make the world a better place. But what does that mean in reality? Well, if you have a positive correlation like this, so you've got maybe a variable on the y-axis here and a variable on the x-axis, for every 1 unit increase in the x-axis, you basically have a 1 unit increase in the y-axis, and that's what creates this this kind of positive correlation. If you were to plot a line of best fit, that's basically what you would end up kind of seeing. That's how you should kind of interpret it. And then on the kind of opposite end of the scale, if it was a negative correlation, so as you increase a unit of x, so you move to the right here, you actually decrease in 1 unit of y, basically, and that's what creates this kind of negative outcome here. So as one variable increases, the other one decreases. So for both of these, we've seen actual relationships, either positive or negative, but then you can also get neutral relationship, so no relationship. And I've seen this a few times where you plot something and there's just no relationship at all. It's just scatter plots, there's just plots everywhere, points, and there's no linear relationship. So that's something that you need to be aware of. Okay, so these are just generalized scatter plots for understanding the different directions. So when we do that, we can start to think about the strength, as I've already mentioned. So this could be a perfect association over here. It's a perfectly positively correlated association between the variable on the x-axis and the variable on the y-axis. Or we could have a strong association, a tightly packed association here. So if you were to plot a line of best fit along here, it'd still be highly positively correlated. Or we could have the opposite. We could have weak associations. So there's much more distance here between if you were to plot a line of best fit, there'd be greater variation either side of it. And actually you do end up seeing this much more. I mean, it's a rarity that you see really strong correlations, or at least from the work that I've done. Or then finally, we've got no association down here. And actually, when I was talking to you on the previous slide, so back here, and we were thinking about these different relationships, I wanted to take you to this point essentially that correlation is measured between -1 and 1. So if it's perfectly positively correlated like this here, it would have a correlation of 1. And if it was negatively correlated over here, it would have a correlation that's closer to -1. Okay? And 0 essentially implies that there's no correlation. So it would be this type of association down here where you don't really think that there is any. And this is how we need to think of it. And actually, it's not that dissimilar from some of those other tests that we've thought of where we've been on a similar scale between 1 and -1. And actually, when you think about the values that you have here, and you can think about them in terms of what I alluded to earlier, which was that if you increase the x-axis, for example, by 1 here on this perfect association, the 1 also then means that you would have an equivalent increase of 1 on the y-axis, okay? And that's the same for the negative correlation. So if you increased 1 on the x-axis here, that -1 means that you decrease your y-axis by -1, okay? So that's just my kind of brief explanation for how to interpret the correlation there for the different values. There's more in the book. Obviously, now what we're going through is a kind of high-level theoretical approach to understanding correlation, but we will then cover more of this within the laboratory session. Okay, and hopefully you'll have a good understanding then of what we mean when we talk about these different positive or negative correlations. And if not, then reach out to me. There's also plenty of material online for correlations which can help you understand this kind of fundamental statistical technique. So the association for the variables can either be linear, so it can follow a straight line. It can be non-linear. So there is actually a non-linear way for you to understand relationships, non-linear based regression, for example. We're not going to cover it within this course, but just be aware of it. In fact, the tests which we are going to cover today in this class actually all assume that there's a linear correlation between the variables of interest that we're actually going to model their variation of. Or you could just have random associations, so that's the no trend, the no association part. Okay, and I've already mentioned that today we're going to be covering linear associations. So that's the background. I mean, the key caveat here obviously is that correlation does not imply causation. And what does that mean? Well, I heard some of you may have encountered this before, but obviously correlation is the amount that two variables vary potentially together, whereas causation actually implies that one thing causes the outcome in another. And actually, when we think of correlation, it does not mean that one thing causes the outcome of another. And this is the kind of standard part in a statistical course where the lecturer will show you examples of where correlation gets mixed up for causation and kind of emphasize the point that you don't want to fall into this trap. Okay, so I mean, we've got some on the right hand side here, which is basically the plotting of Microsoft Internet Explorer's market share between 2006 and 2011 and the murder rate in the US. Okay, so we've got the murder rate on this left-hand y-axis, and we've got the market share for Internet Explorer on the right-hand side of the y-axis here, and they're pretty much perfectly correlated, but obviously one doesn't cause the other. Okay, and I could give you many examples of this. So there's another one down here, which is the number of people who drowned after falling out of a fishing boat in purple, and then there's the marriage rate in Kentucky. Okay, so you've got the death rate here for people falling out of fishing boats on the left-hand y-axis, and you've got the marriage rate in Kentucky on the right-hand side, and you can actually go to this website. So if you look up tylervigan.com, he has a whole website just on spurious correlations. So correlations which definitely don't imply any sort of causality, but are really nicely correlated together. So I think it's definitely worth you kind of looking at that, because this is a fundamental point that you need to understand, and there's some kind of fun ways to understand that based on these kind of silly graphics that people have created in order to kind of bring this statistical point to life a bit more for people to learn. So this is just kind of picking up the fact that we may have variation that takes place between two variables. It doesn't mean that they're causally attached. And very often, actually, there could be a third variable which you just haven't measured or isn't in your data set, or you haven't plotted because you're only plotting on two axes, which is really causing these two variables to vary in the way that they are. And this is just so common. I mean, every time you do a paper which focuses on correlation or regression, these are the types of questions which people are going to ask you about omitted variable bias, for example. Do you have a major variable that's omitted from your data set or your model which just isn't included and therefore may be driving certain outcomes? And if there are multiple variables in the data set that have similar associations, then there may be a problem of multicollinearity. So that's when you have lots of correlation within those different metrics that you've got, and that can cause some problems for then how you carry out regression further on down the line. Some of the models that you might want to use, we'll cover that at a later stage. I don't want to get too much into it today. And in terms of geographic examples of correlation, I just chose this kind of joking example here because it was funny and I thought you might enjoy it. So this is a good example of when correlation does not equal causation. So on the left hand side here we have all of those places that voted in the UK to leave the European Union, so the British exit, Brexit voting areas. So the people who voted to leave were in blue here, and the people who voted to remain are in gold and yellow. And actually, if you then compare that outcome, which is relatively recent, with the areas in 1992 that had lots of cases from bovine spongiform encephalopathy, which is basically known as mad cow disease, and people got it basically from eating low quality beef. And the funny thing, of course, here is that the areas are pretty much entirely correlated. So you'll see like some of these leave areas in this part of Northern Ireland, Scotland, something completely different is happening here. And then those places in England that voted to remain or didn't have BSE are generally all of the urban areas. Probably more wealthy as a bit of an indicator to you, probably higher socioeconomic status. Whereas then the areas that voted to leave and which had lots of mad cow disease cases were generally these kind of poorer rural areas. And this is a good example of the kind of omitted variable bias, or the third variable which I alluded to up here. So ultimately what I'm alluding to here is that the socioeconomic status of different places actually affects maybe how people vote. Also, it might affect how they buy their meat and how they might actually contract diseases like mad cow disease. And that's an important variable which we haven't included if we were to just spatially look at these two different maps. So I hope that I've made this clear, that you need to be kind of cognizant of what you're actually mapping and whether that you've caught all of the variables that may help to try and describe the process which you're trying to understand. So let's move on now to the actual statistical tests. So covariance essentially is parametric correlation. It relates to, covariance is parametric correlation essentially. So it measures how two variables vary together. And we've got good examples over here of positive correlations, negative correlations, and very low covariation just down here. But how do we actually calculate that? Because we've been talking in high level qualitatively about this, but we haven't really gotten to the nuts and bolts. And what we're showing here within this this equation essentially is the covariation between two different variables, so x and y, and how we actually obtain that. So essentially we need to take the deviations of x from its mean. So we've got x bar as the mean here, and we need to subtract that from each from x value, and the same for y as well. So we need to subtract the mean of y from y to get the deviation of y from its mean. And you'll remember that this type of mean deviation is essentially the key building block for how we calculated a standard deviation and standardized scores in some of those other tests which we calculated earlier within the course. Okay, and once you get that, you're then able to calculate this covariation metric between these two different variables of interest. So that's covariation. We're now going to follow on to what that actually means in terms of testing for correlation. So we hang on to the fact that we covered covariation. We will bring it into the tests which we're going to cover within this section of the lecture. So when people talk about correlation, really they're kind of talking about Pearson's correlation coefficient, okay? And that's what we're going to cover here. So this is the parametric approach, so that the approach that assumes that the data are normally distributed. And actually there are multiple different ways that we can calculate Pearson's R, which is the value which we're going to calculate on this slide and then use as we test further on within the class. So we want to calculate Pearson's correlation coefficient here, R of xy, which we do over here basically. So we want to get this R value. And we're going to use the covariation for these two different metrics and divide it by the number of paired samples, the paired data values that we have, to get this numerator, which then allows us to basically divide it by this denominator which we have, which is Sx and Sy, which is the standard deviation of the two variables of interest, so x and y. And that, when we then basically run through that math equation allows us to produce the Pearson R value, which is the correlation coefficient, which then we're able to use as we progress further. And if you read in the book, there are multiple ways to calculate this, and I'm not going to cover all of them here. You can cover them in the book. There's up to 3 different ways that you could possibly calculate it, which are reported, and that's just useful background knowledge for you, but I'm not explicitly going to test you on it. So what do we do within this correlation analysis approach? Well, essentially we are trying to determine if there's an association which exists between 2 variables, okay? And there's a set of assumptions that we need to meet, as with all of the other tests that we've carried out. So we need to have paired variables that have data obtained through random sampling. We need to have variables which assume to have linear association. So if you expected there to be a nonlinear association, this wouldn't be the right type of test for you to use. We would assume that the data would be ratio or interval based, so it would be continuous measure, and that essentially the 2 variables have a bivariate normal distribution, so they're normally distributed for the parametric test. And before we then get to the test statistic, well, what are the types of hypotheses that we would be able to state? So the null hypothesis essentially is that this rho value is the same as 0, so there's no association, basically. Remember before we said that we're measuring correlation between +1 and -1, and therefore the 0 value in the middle indicates that there's no linear relationship between the 2 variables. So that's why our null value is 0. Then obviously we have the alternative hypothesis, the 2-tailed approach, which is that our rho value is not equal to 0. So it could either be a plus or minus, but it's not equal. There's some sort of effective relationship taking place. Or we could have a range of alternative hypotheses which are 1-tailed, so directional. So we could assume that we could state that our rho value is larger than 0, so it's positive. We think there's a positive correlation. Or we could assume that our rho value is below 0, so there's a negative correlation. And we use the t-statistic. And importantly, the number of degrees of freedom relate to the number of pairs of observations that we have, -2. Okay, and to get the t-stat, we basically need to take this denominator. So we need to get the R value, so Pearson's correlation coefficient from the previous calculation, and then we need to multiply it by the square root of the degrees of freedom. That helps you get the numerator. And then for the denominator, we need to take the square root of 1 minus the correlation coefficient squared. And that should provide us with the t-statistic that then allows us to carry out our standard hypothesis testing approach. So we're able to exogenously specify an alpha value, which gives us a significance level for a p-value that then we can evaluate to say whether we have significant evidence that there exists a relationship, or whether we don't have significant evidence to reject the null hypothesis. Okay, so hopefully none of that's kind of new to you. It shouldn't be too new, because a lot of the concepts behind this, how we do hypothesis testing, how we evaluate significance, how we state hypotheses and evaluate them, this should all be kind of ingrained into you now that we've covered this in so many other examples. So we'll cover this within the laboratory session. We'll be able to work out some of these calculations by hand within the R code, as well as comparing it to some of the kind of inbuilt statistical functions that we have within R. And what happens then if we have non-normally distributed data? So if we have a non-parametric correlation, then Spearman's rank correlation coefficient is the most appropriate approach for us to use. So this is particularly applicable if we have monotonic relationships, so essentially where we have relationships between variables that are either non-increasing or non-decreasing. As you kind of see here, there's some examples of monotonic relationships. And if that is the case, then we may need to convert the data, so downgrade it to rank data in order to make it linear. So we need to get the R correlation coefficient, the Spearman's rank correlation coefficient just down here. And to do that, we need to take the sum of the squared differences in the ranks, okay? And then we need to run it through this calculation. So 6 multiplied by the sum of the squared differences in ranks for the numerator. And then we need to get the denominator, which essentially is the number of paired data values cubed minus the number of paired data values, and that should give us the equation that we need once we subtract the outcome of that fraction from 1 to actually get the metric of interest that we want. Okay, and so just in case, because I might not have mentioned it, the D value here is the difference in the ranks of variable x and y for each paired data value. Okay, so I hope that's all clear. You've got all of the key ingredients in order to run through that math, and hopefully we'll be able to run through that in the lecture, and that should become clearer to you. So we're going to take this R value forward, this Spearman's rank correlation coefficient. We're going to use it within the actual formal test, which allows us to understand if there is a correlation between these two variables in a non-parametric fashion. So what are the assumptions? Well, we assume that the paired variables that we have come from a random sample. We are going to use ordinal observations, remember, because we basically decided that if our interval or ratio data, for example, weren't normally distributed, maybe they were monotonic, maybe they didn't meet some of those assumptions that we needed to carry out Pearson's correlation coefficient, then we would have to downgrade that data to ordinal. And then also the two paired variables of x and y have a monotonic relationship. So what's the hypothesis? Well, essentially the null hypothesis is that our rho value is equal to 0, so there's no statistical relationship between these variables. Well, the alternative two-tailed hypothesis is that our rho value isn't equal to 0, and therefore it could either be a positive number or a negative number. Or we could have the one-tailed directional hypothesis, so our rho value could be larger than 0 if we think that there's a positive correlation, or our rho value could be lower than 0, smaller than 0 if we think that there's a negative correlation. Okay, and then the test statistic, depending on the sample size, is z, for example, and the number of degrees of freedom also is n-2. And that allows us to then carry out this calculation. So we want to get the z test statistic for this particular correlation coefficient, the non-parametric version. So we need to get the RS, multiply it by the square root of n-1, and that should give us our test statistic, which then we're able to evaluate in the standard way in which we evaluate hypotheses. Okay then, so I think that this has covered quite a bit of ground today. I'm looking forward to going over this in the lab with you because this is important information. So we've covered the kind of high-level math now, and now we're going to go through in the RStudio session and basically actually work out the calculation of some of these metrics in some code. I hope that you're finding the code easier to command now because I think there's that little bit of a learning curve for you guys to kind of jump up to the command line. But I feel like in the lab sessions, we're kind of able to go from the math, which maybe some people aren't always that comfortable in reading, to understanding kind of in a very simple way what the actual math instruction is in order to get that metric that we're interested in. And I think that that's a really nice way to do it. Okay, right, well, that's the end of this lecture, so the 13th lecture for GGS 300. I'll look forward to seeing you in the laboratory session, and I hope you're all well. Let me know if you've got any queries about this lecture, and I'll see you all soon. So thanks for tuning in. Goodbye.